everybody, we are back and we are going to do problem set 7 solutions. So, which material is the stiffest? So that's the one with the highest slope. So actually, let's zoom in here just a little bit. So that would probably be my blue curve. It looks like just a little bit steeper. Blue or the light green, so. My toughest, I would say that probably because this black curve is the highest, and if I look at the total area in the curve, this is not too much different, I think the toughest is going to be my black curve. Strongest, well, again, depends. Am I talking about, actually it says here UTS strength, so that's also black. Highest yield strength, well, let's look at that here. I actually think that, yeah, it's actually black curve as well. Most ductile, black is the highest yield strength. Most ductile, that's going to be my green curve. Most brittle, that'll probably be the, like the blue or the purple. So, purple. So there you go. Again, basics of your stress strain curves. You can kind of look and see those values. For the black curve, indicate the quantitative value of the failure strain. So the failure strain, that's probably about 10%, or basically 0.1 strain. Failure stress, that looks to be about, I'd say about 1800 MPa. So we got that. Yield strain. So my yield strain, let's say it's about here. It's about 0.02. My yield stress, about 1600 MPa. And then ultimate tensile stress, I'd say it's probably about 2000. So make sure you have all those values down. Excellent. For the following stress state, draw the RVE element and the forces. Be sure to include a coordinate system. So I've got my 1, 2, 3. Draw my cube. This. So I have a stress in the 2, 2 that's positive. I have a stress in the 3, 3, which is negative. And then I have a stress here in the sigma 2, 3. So again, normal in the 2 direction and positive here. So actually let me go like this. And then opposite here. Where else? Again, 3, 2. So again, positive in the 3 direction, moving in the 2 direction. So it'd be like this, and then like this. So there you go. That would be our RVE. So draw the Mohr circle for all these different planes, and then we're going to go about kind of solving it. So let's draw 3 more circles, and then we don't need to necessarily draw more circles, but we can answer this question this way. So I'm going to look at these different colors. So I'm going to look at this plane, I'm going to look at this plane, and then I'm going to look at this plane. So let's start with some nicer ones first. So for my 1, 2 plane, one more circle is just going to look simply like this. So I've got, let me erase. I've got 21 MPa. These are all again in MPa, and then I've got 0. So I'm already in my principal stress state. So my sigma 1 is equal to 21 MPa. My sigma 2 is equal to 0 MPa. So I've got that. Determine the rotation to get to principal and maximum shear stress state. So principal 0, to get to maximum shear, it's going to be 45 degrees because again this is 2 theta equal to 90. Write the full stress state for a clockwise rotation of 13 degrees from the maximum shear stress state. So I can do the following now. So I'm going to pull up my Mathematica. I'm going to write down my sig 1, 2 equals 0, 21, 0. And then I want to do, so 13 degrees clockwise from the maximum shear stress state. So if I look at this particular problem, so I want to do 13 degrees clockwise from that shear state. So if I'm looking from here and rotating to here, it's going to be 45, actually plus 13. So if I look at that full clockwise rotation. So, or I can look at it from the other way. So again, you can solve this problem multiple ways. And actually, we could look. Actually, we'll do that together right now because this is an interesting one to do. Let me pull this back up. Let's pull back this guy here. So I could do it a couple ways. So I could do T, capital T, T dot sig 12 slash dot theta goes to 45 plus 13. I could look at this numerically. I can do T sig 12 slash dot theta goes to 45 minus 13. I can look at this numerically as well. So you see all I'm doing is it's flipping here. We still have the same values. So these are equivalent stress states. I could also look at basically the max shear and rotate that way, but you'll see the values are exactly the same. So we got it. So first plane is done. What about the next plane, the 2, 3? Actually, no, let's not do this. Let's do the 1, 3. So I'm going to do, oops, let's go over to draw. I want to do tau. This is going to be my sigma of 1, 3. And now I'm going to get my 1, 3 planes. So in the 1, 3, I just have a 0 here, and then I have a minus 87 for my coordinates. So again, in my principal stress state, so 0 degree rotation, 45 to get to principal stress, and it's the same kind of idea here. My sigma 1 in this problem is equal to 0 MPa. My sigma 2 is equal to minus 87 MPa. And I can go that sig 1, 3 equals 0, minus 87, and 0. So I've got those. T dot sig 1, 3 slash dot theta goes to, again, the same thing, 45 plus 13. Let's look at this numerically. T dot sig 1, 3 slash dot theta goes to 45 minus 13. And let's look at that numerically, and we'll get the same values. Excellent. So now on to the harder one, effectively. So let's go ahead and look at my tau 2, or actually, excuse me, 2, 3 plane. So now I've got tau, I've got this. So now I've got a more complex stress state. So I've got basically a point at 21, a point at minus 87, a point at 15 here. Let's get that a little bit closer. Erase, erase, erase. Point at 15, point at minus 15. So I've got 4 coordinates here, 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 and here. Due to circular symmetry, the circle must pass through this. And now I'm looking at a stress state like this, and I need to find the rotation to get back to my principal stress state, 2 theta. So I could solve that with more circle, or again, I could take my linear algebra approach. So my sig 2, 3 is equal to 21 minus 87, and then 15. So I've got that. I can basically take T dot sig 2, 3. I could take this, and I want to look at, because I know my principal stress state is when my shear stress, or my third component here, will be 0. So let's go ahead and solve that equation. My third equation here, set it equal to 0 in terms of theta, and let's do numerically solve. And I could find that rotation. So pull out these values. Again, either any of these values are just going to work. 7 degrees. So I need to do a 7 degrees clockwise, counterclockwise, excuse me, rotation to get that principal stress state. So what's the value of my principal stresses? Sig 2, 3 slash dot theta goes to this. And that's pretty much 0. Boom, boom. We've got it. That's my sigma 1, 2. That's my sigma there. So what about for my maximum shear angle? Well, to get to my maximum shear stress, I could just take this equation. I want to set the derivative with respect to theta, so I want to maximize theta now. So I've got my angle here that maximizes theta. So I could do T dot sig 2, 3 slash dot theta goes to this. And center, center, and then this is my radius, my maximum shear. Fantastic. And again, if I want the stress state, again, 13 degrees clockwise from this, I could just do, again, from this stress state, from this maximum stress state, I do minus 13 because it has a clockwise rotation. So I'm looking at that rotation to get to maximum shear, and I can just do minus, and there it is. There's your answer. So we've got all those values, and now it's asking us to do the kind of our more circle. So now I could do sig general is equal to 0, 0, 0, 0, 21, 15, and we're trying to find our principal stress state in three dimensions. Minus 87, and there we go. So I can simply do eigenvalues, sig, And these should be my principal stress values. But we could also check this from our work previously. So looking at these values, sigma 1 and sigma 1. So what's the largest sigma 1 value we have? So, and then again, remembering this one here too. So 23 is the largest sigma 1 value. What's the next largest sigma 1 value? Or actually, not the next largest one. So what's the next largest sigma 2 value? Excuse me. So sigma 2, what's the maximum sigma 2 value? Sigma 2, that'd be 0, right? So we got the 0 right here. And then the lowest value of sigma 2 is the minus 989. So we've got our values. So these would be our principal stress values. This would be sigma 1, sigma 2, sigma 3. So you just draw the Mohr circle around that. So tau, this, sigma 1, sigma 2 here, 0, and then sigma 3. Circle, circle, circle. And then, again, our radius or our maximum shear stress would just be sigma 1 minus sigma 3 over 2. So there we go. We've got it. So we've given the quantitative values, and now let's go ahead and see. We need to kind of zoom in here. Let's zoom in what the problem says. So we've done number 3. We've given the quantitative values. Material in the above problem is actually the black curve from the first. In the loading state, will the material yield via the von Mises, Tresca, or Rankine criteria? So the black curve, we just said the yield stress was about, what was it, 1600 MPa. So we found that sig 1 was this. Our sig 2 was 0, and our sig 3 was this. So, with that being said, now I can start to see, so my Rankine criteria is saying that if my sig y, which is equal to, and I need to multiply all these, because these are all in MPa times 10 to the 6, and then times 10 to the 6. So sig y, I'm going to ask, sig y is equal to 1600 times 10 to the 6. Is sig y, or actually is sig 1 greater than sig y? That's my Rankine criteria. No, it will not yield. Is sig y, or is basically sig 1 minus sig 3 greater than sig y? Nope. And then the von Mises, annoyingly, so 0.5 times sigma 1 minus sigma 2 squared plus sigma 2 minus sigma 3 squared plus sigma plus parentheses sigma 3 minus sigma 1 squared, close it and square root it. So is this greater than sig y? Nope, so none of them are going to yield. There we go. So let's look at the cubic mold problem. I like this one. So I'm looking at this cubic mold. It's closed at the top, but it's open, so we're open in the one direction. So the material can move out in the one direction. We're well lubricated. I think the mold is basically 100 millimeters in shape. So I'm working with zinc. So zinc is a metal. So I know that my Young's modulus is equal to 100 GPa. I know that my nu is equal to 0.3. So I've got those values down. And it's saying I'm applying this stress. And now I need to figure out what are my quantitative values, what's the value of force required to move it, so all those other good things. So I am definitely applying a stress in the 2-2 direction. Actually, let me erase this. Give me some more room to play around with. So when I'm looking at this material, again, I'm closed at the top. So the top is closed, and the top and bottom are closed, but I'm allowed to move in the one direction. So if I look at my stress state, I'm definitely going to have a stress in the 2-2. And then for the strain, I'm also going to have a strain in the 2-2. And my strain in the 2-2 is going to be equal to 1 millimeter, which is my final distance, minus 100 millimeters over 100 millimeters. So let's take a peek at those values. So I'm going to actually calculate that already. So again, I'm always wanting to kind of quit my kernel whenever I start these problems, because I want to clear everything out. So my y is equal to 100 times 10 to the 9th. My nu is equal to 0.3. My E22 is equal to 1 minus 100. I should be multiplying this everything by 10 to the minus 3, but I know that I can deal with that. So I know this value, so I've got this one. I don't know this value. When I push on here, will there be a stress in the 3-3 direction? Yes. Will there be a strain? No, because it's closed. What about in the 1-1 direction? No, there will be a strain here, and I don't know this value of 3. I don't know the value of the strain in the 1-1, and I know that the force in the 1-1 will be 0. So everything else, because we are well lubricated, will be 0. So I could start to say that my sig 1-1 is equal to 0, my E33 is equal to 0, and now I have 3 unknowns, but I can write 3 equations. Solve E11 set equal to 1 divided by y times sig 11 minus nu times sig 22 plus sig 33, and then copy and paste. But I need to change some of those values. 1, 2. Close it. What do I want to solve for? I want to solve for the E11, the sig 33, and the sig 22. So this is E22, this is E33, E33, this is sig 22, this is sig 11, sig 33 will be 11, and this is sig 33. Solve that. Does it make sense? Yep, the material is expanding that direction, compressed in the 3-3 direction, compressed there. Everything's looking okay to me. So we've written out the full stress and strain tensor. What's the force required? So I'm going to solve that my stress, which is in the 2-2, my stress is equal to my force divided by my unit area, which is 100 times 10 to the minus 3 squared because it's a cubed. Solve our force. That's quite a lot of force, which we might expect because we're reducing that quite a bit. We're definitely plastically deforming that material. Excellent. So now let's move to the next problem. I'm trying to design a new material for water pipes in my house because I'm worried about the last flood. I have pipes with a diameter of 35 and a thickness of 8K. So whenever you see those values, when you hear those words, diameter and thickness, alarm bells should start to go off. What problem am I working with? You guessed it. Frank Stallone. No, thin-walled pressure vessels. So my diameter is equal to 35 times 10 to the minus 2. So my radius is equal to diameter divided by 2. And my thickness here is equal to, what is my thickness? 0.5 millimeters. So equals 0.5 times 10 to the minus 3. So if I'm thin-walled, my radius divided by my thickness is going to be greater than or equal to 10. And if that's the case, then I can move directly to my thin-walled pressure vessel expressions. Whoop, we are definitely thin-walled. So I know that my stress tensor here will be my sigma 11, will be my sigma hoop, my sigma 22 will be my longitudinal, everything else is 0. If I want to find my hoop strain, it is going to be equal to 1 over E times sigma H minus nu times sigma L. My strain in the L is going to be equal to 1 over E times, or 1 over, sigma L minus nu times sigma H. And I know that my sigma H is equal to del P R over T, and my sigma H is equal to 2 times sigma L. So I can start, and actually I'm going to go ahead and write this expression right now. So sigma H is equal to del P times R divided by T. Sig L is equal to sig H divided by 2. My EH is equal to 1 divided by Y times sig H minus nu times sig L. My EL is equal to 1 divided by Y times sig L minus nu times sig H. Excellent. So let's see what else is given in the problem. San Joaquin County claims the pressure exerted on the wall of the pipes must be approximately 26 megapascals. I've developed a new material that when stressed under these conditions will exhibit a strain in the 2 direction of approximately 0.01 and in the 1 direction of 0.08. So in the 1 direction, so basically I could go ahead and solve. So right here I have 3 unknown values, but we're told that basically our del P is equal to 26 times 10 to the 6. So that's the MPa, the pressure that our pipes are under. So with that, I've got my sig H, got this. So I'm left with 2 unknowns, but I'm given the values of EH and EL. So I can go ahead and solve for 2 equations, 2 unknowns, solve for them simultaneously. So in the 1 direction, that is my hoop direction. So EH set equal to 0.08 and EH equals 0.08. And then EL set equal to 0.01. Solve for Y and nu. Let's do that. And we've got our values. Excellent. We found the Young's modulus Poisson ratio, full stress strain tensor. What's the maximum value of shear stress? That is just going to be, again, as always, sigma h over 2 for my tau max for this problem. Rotation, principal stress, 0, maximum shear, 45. What's happening with this fracture? So actually, it should fracture like this, so this has to be some impurity or defects or something else happening here. So something weird is happening. When a material fractures, what are two energy contributions that determine what will be the critical crack size? So again, this is going to be your surface area creation and your elastic strain energy relieved. For this problem, what is the critical crack size, and justify your selection of the fracture equations based on the material you would want as a pipe. So we want to think about what material do we want as pipes. Now, typically you've worked with, or you've probably seen copper pipes. So that was kind of your usual kind of mechanism, or some of the old. I mean, you hopefully definitely don't have lead pipes. That would be very bad. But typically you're dealing with metals, and then now the kind of new and actually better material, to be honest, is like these PEX piping. So PEX is basically just a polymer piping, and so they're actually really, really great because they resist fracture and all these other things. So the question we have to ask ourselves whenever we're dealing with fracture mechanisms is we have two fundamental equations that we utilized in class for a fracture. So those being our OR1 and our Griffith criterion. So if we remember back from our notes, when we're looking at the fracture mechanisms, the Griffith criteria was applied to what types of materials? Well, they were applied to brittle materials. Now, the metals that use in pipes, are they particularly brittle? No. So the Griffith criteria is not applicable here. Instead, we're going to use our OR1 criteria, which is going to be our sigma F is equal to square root of EGC over pi A. So again, I know this material now, so I know actually that my GC, my elastic strain energy, is going to be, so we see that our elastic strain, our strain energy release rate is 75,000. So let's start to kind of assign these values. So let's go ahead and plug those in here. So we got this in here. Here's our Young's modulus. Our G value in our OR1 theory is going to be equal to 75, 1, 2, here we go. And so now we could go ahead and start to solve. So we are told here, again, we're trying to find under this stress state, what's the critical crack size? So I'm going to figure out our highest stress, our sigma 1, which is also sigma h. So I'm going to solve the stress at fracture. Let's just say, again, for example, sigma h, ch, set it equal to square root of Young's modulus times g divided by pi times a. Solve for a. And this would be the critical crack size. So about 2 micrometers, 2.6 micrometers, that would be the critical crack size that cracks. All right, label the deformation mechanism maps. Well, we know, let's get into here. This is my theoretical. Actually, I'm just gonna do this. 1, TS, 2, dislocation glide, 3, elastic, 4, Coble creep, 5, Nabarro herring, and then 6, power law creep. So I'm gonna do 6, 6, and 6 and 6. This is going to be 2, 2, 2, and 2, 3, 3, 3, 3, and then if I look down here, the Nabarro herring is going to be 5, 5, 5, 5, and that just leaves 4, 4, and then 4 here. So excellent. So we've labeled the deformation mechanism maps. All of them are, let's see. Under what conditions will Coble creep, PLC, and H dominate? So remember, Coble creep, it's when we have small grain size, dg to the minus 3. Nabarro herring will dominate at very, very high temperatures. PLC dominates when our stress is 4 to the 6th power law scaling. So, and again, we've gone through in class and in other videos in terms of Coble creep, we're looking at the diffusive pathways along those grain boundaries. So the more diffusive pathways, the larger the kind of total strain rate. For Navarro herring, we're looking at very, very, very large grain sizes, so diffusion, the bulk dominates. And then for PLC, we have high enough stress to kind of move those. So again, here we're still applying a resolved shear stress that is less than my lattice resistance. So draw the stress curves based on the deformation mechanism maps below. So I know if I'm going to label this 1, 2, 3, 4, my yield strength of 4, 1 second here, actually let's zoom out. I know that my yield strength of 4 is greater than my yield strength of 3, which is greater than my yield strength of 1, is greater than my yield strength of 2. So I have those yield strengths, so now I can start to draw that deformation mechanism, or the stress strain curves. So if I draw the stress strain curves, not the yield stress, just stress, strain. So my 4 will be, and basically, again, these are all the same material, so basically this would be 4, and then it'd be basically 3, 2, or 1, and then 2. Excellent. What are the 4 different types of strengthening mechanisms? And describe the scaling. So for cold work, we have change in yield stress scales with dislocation density to the 1/2 power. For solute strengthening, we have the change in yield stress scales as C solute to the 1/2 power. For grain size strengthening or Hall Petch, grain size, we have this scales to the DG to the -1 up to 10 nanometers, below which, again, that starts to break down. And then we have our precipitate strengthening mechanism. We don't have an essentially scaling there. But if we look at it here, we'll have a curve that looks like this. Actually, it looks like this and like this. So this critical radii. If I have precipitates, I want to cut small radii. I want to bow around large radii. So because cutting creates surface area, bow is related to kind of our curvature, and then that's it. Excellent. Big problem set 7 done. Congratulations. I'll see you all in the next video. Thanks. Bye.